about closed cosmologies from the CFT, so please.
Right, okay, so let me start by thanking the organizers for giving me the opportunity to present this work here, and also for putting together this super nice conference that I'm enjoying a lot, even though it may seem that there were some accidents and so on. But I mean, if you don't play football on the beach, all the rest of the things are very nice in Natal. So I encourage you to do them. So okay, I'm gonna talk about like a way to study closed cosmologies from the CFT in an ADS CFT context. This is work recently put out with Stefano and Martin, who are here in the audience, and Pratik Rath and Brian Swingle. Okay, so let me just say some words of introduction. So closed cosmologies are confusing beasts. In principle, we could be living in one, but trying to develop a quantum gravitational description for them leads to puzzles. And if you want to see some of these puzzles, I encourage you to have a look at the nice talks presented last week by Misha and Vincent. Okay, I'm going to make some comments along my talk about these works as well. They are not like super essential for those of you who are not here, but still I encourage you to have a look at the talks. So the idea today is to review and expand on a setup that allows to discuss closed cosmologies using area CFT language and techniques. And to say like the outcome at the start, what I'm aiming for is to present a picture where the arguably embarrassing result that the Hilbert space of closed cosmologies is one-dimensional is somehow reinterpreted. It's not going to be exactly avoided, but it's going to be reinterpreted, okay, using input from the conformal field theory in area CFT, okay? So that's the goal. So the outline, I'm going to start presenting the setup and the states that I'm going to be discussing throughout the talk. Then I'm going to discuss the holographic encoding of the closed cosmologies and connection to some observer proposals. This is going to be fairly conventional by now. Then I'm going to move on to a part which is more speculative, if you will, in which I talk about the intrinsic description of the closed universe. And time permitting, I will also mention like some other ways to see the closed universe from the CFT that involve like coarse graining. Okay, and I will end up with some final comments. So please like interrupt if you have questions at any point. Okay. I mean, it's going to be a bit difficult for me to control all the room, but hopefully you can just interrupt. Okay, so setup. So we start from two pairs of low energy entangled states in a holographic CFT, okay? And each pair of these is dual to two global ADS regions which can be entangled, which can have matter which is entangled between them, okay? So notation, I have like a CFT big L here and a CFT big B, and I'm thinking of a state between this ADS small l and small v, which is entangled between them, right? So for example, a typical example of this would be you prepare a thermofield double below the Hawking-Page transition, okay? So when the dual is two ADS regions. The Euclidean preparation is going to be useful and used a lot, but it's in principle not essential, okay? You can consider any other state of two ADSs which is entangled and the dual CFT state, okay? So I did this for this pair. You do that again for another pair between C and R CFTs, okay? So notation, big psi's are CFT states, okay? I have like a bulk state, which is a small psi. And these V's are like the usual holographic isometries that you have when you have low energy states on ADS that basically map bulk states to the boundary, okay? So I can see like the CFT state as the image under this isometry of the bulk entangled state, okay? So I'm considering low energy states, and in particular, you can drop any possible states in the high energy region, okay? So for example, if you do the thermofield double preparation, you have like high energy stuff as well. Very small parts of the wave function are there, but you can drop those because like the wave function is mostly localized in the low energy region, okay? So I'm considering, I'm implicitly doing that. I'm not considering energies that scale with n squared or something like that, okay? Now, second step. So we glue B and C, remember these middle two CFTs, through a spherically symmetric Dust shell operator. Okay, Dust shell operators are something that were studied in other papers previously, in particular these two here. So these are basically operators that are localized along a sphere in the CFT at a particular moment of time, and they create like a thin shell of dust in the bulk, okay? So they create like some matter that has like basically this energy, the stress energy tensor like this, localized in the wall volume of a shell, okay? These shells are characterized by a certain mass. Now, from the CFT, you can think of these operators as many insertions of primaries in a way that is spherically symmetric. Okay, I don't want to enter too much into this discussion. This was discussed in these previous papers a bit, and it would take me a while to enter into that discussion. But in principle, you can try to do definition from the CFT as well of what these operators are, okay? So what does it mean that I'm gluing B and C using this operator? Okay, basically in my previous slide, I had this preparation in the CFT where I had L and B and then C and R. And what I'm doing is gluing B and C and inserting this spherically symmetric operator O that creates a shell in the bulk, okay? Now, this is just a fancy way of writing that insertion, okay? Now, these states were studied, like for the setup I described in the previous slide, so when you are below Hawking page in this paper, but similar states were considered also in other setups, like for example in this paper here for black holes when you go above Hawking page, and previously in 2 dimensions in this paper by Herman and collaborators in 2018, yeah. Right, so in my case, what happens in the bulk? Okay, so I have my preparation here, I glue B and C through this spherically symmetric thin shell operator, and I have my R here, okay, and each side of this shell is basically like gives you 2 ADSs, as I was discussing in the previous slide, okay? So when you insert this shell, basically the geometries get glued via the Israel junction conditions, okay? And the state that you prepare in the time symmetric reflection slice is a state on one ADS L. The other 2 ADSs that I had get glued through the shell and give me some closed cosmology. There's no boundary here, okay? This is an R equals to 0. This is another R equals to 0. A sphere grows, grow. They cross the shell and they start decreasing and go back to R equals 0. This is a compact closed cosmology. And then I have a right ADS region as well, okay? So yeah, and if you take this and do the Lorentzian evolution, you get an ADSL here, a full ADS, global ADS as usual, another full ADS there, and then you get like the closed cosmology that collapses on the thin shell, okay? So this is a cosmology which is not homogeneous because like there's a matter concentration here that's what's supporting the cosmology. So for example, it's not like the typical homogeneous FRW cosmology, but it's still a closed cosmology. It's a model of a closed cosmology, okay? So why not? Okay. Right, so these states are characterized basically by 2 parameters, okay? One is the mass of the dash shell that you use, and this controls the size of the closed universe. Don't look too much at the details here. You can look at this, you can compute this carefully, but basically this R star tells me how big is the sphere on which the shell is inserted, so how big my cosmology is, basically. And at very large masses of the shell, I can make this as large as I want, okay? So I can have like a very big closed cosmology by taking the shell to be very heavy. I can also make my cosmology to be sub-ADS, meaning smaller than the ADS scale, okay, within some other parameter range. It's not very important. And then the energy of the state in the CFT controls how much entanglement I can have between the closed universe and the external ADS regions. Why is this? At a certain energy, I have a certain number of states in my CFT, which below Hawking page is controlled by the density of states of a gas in ADS, okay? So it scales like this. And I can use all those states to entangle with my cosmology. So this tells me how much entanglement I can have, okay? This is true up to the point where the black holes start to be like the dominating phase in the microcanonical ensemble, okay? So I can use this up to energies that scales with n, not like n square, but still scale with n. And what this means is that I can also have entanglements that scale with n. Not like n square again, but I can have pretty large entanglement, okay? I can have like a scaling with n. We will assume we are in this situation for a while, like at least while I talk about the holographic encoding, okay? Right, so a small plot of what's the parameter space of solutions here. So my states look like this at a certain time slice. I have like an L ADS region, an R ADS region, and I have like the cosmology, which is entangled with them, okay? And I have like 2 parameters, the mass of the shell and the energy of the state in the CFT. Now, if I make the mass of the shell too small, the cosmology becomes Planckian or smaller, and I don't trust this, okay? So we will never be here. Now, if you increase the mass of the shell, you can have like cosmologies which are sub-ADS or super-ADS, okay? And when you increase the energy, what this allows you is to have more and more entanglement, okay? So in particular, the colors here, I don't want to be very precise. You can have a look at the paper if you want to understand exactly what they mean, but basically the idea is that here in the green region, you can have a lot of entanglement for a sufficiently small cosmology so that you will be able to do like some sort of isometric encoding, okay? While in the blue region, you can have still a lot of entanglement, but the cosmology is also very big, so you will not be able to isometrically encode it, okay? That's basically what these colors mean. Let me say also that if you go above in energies, I'm just considering the part of the states, so this the parameter space in which I have like disconnected ADSs in the beginning of my construction. But if I start going up in energies, what happens is that instead of having this L and B disconnected ADSs, the dominant saddle becomes a black hole. And then the kind of states that I construct are basically states where this thing, instead of being the cosmology, is a black hole interior. Okay, these entanglement lines become like an actual horizon, and I get a connected geometry. Okay, this was studied in this paper by Vijay Balasubramanian, Albion Lawrence, Javier Magan, and Martin Saciet, and we expanded a bit on that with Roberto and Anna in a follow-up paper. Okay. Okay, so I will move now to the holographic encoding. How the states in the cosmology are encoded in the conformal field theory. Okay, so for this, to motivate this, I will use the standard isometric encoding of low energy states in the CFT. When you have an ADS with some particles in it, you can encode that state in the CFT isometrically via HKLL or something like that. Okay. Okay, so let's start going like step by step in this equation. So I constructed my state by actually projecting on B and C this state of 4 CFTs. Okay, this is the thing that glued the CFTs, including introducing a thin shell operator. Okay, so this is the picture that I have here. Now, suppose I write these states of the CFT as the images under the holographic isometries of some bulk states. So I have my entangled state of L and B, like this thing here, and I have my entangled state of C and R here. And I'm using these isometries to map to the CFTs. The L and R part goes through because this thing is not touching those CFTs, while this V, B, and VC stay here because they are affected by the projection. Okay, so a nice way to look at this part here, at this matrix element, if you want, is by doing like a more local tensor network model. Okay, so you can do like a more local, a tensor network model local at the ADS scale of the B region and the C regions. This is basically what I'm trying to draw here. This would be like a meta tensor network that reproduces these ADSs. I have some state in the B part, I have some state in the C part, I map them to the boundary, and then I project to this shell operator. Okay, this is what's going on here, basically. Now, you can also use these isometries in the opposite direction, mapping this shell operator thought as a CFT operator to a bulk state, okay, and do the projection like in the bulk effective field theory. This is what I'm doing in this final step here. So I'm basically taking the B dagger of this, the dagger of these things, and acting on O, and I get to this final step, okay? And then this final step tells you basically how the information is encoded in the CFT, which is basically like this. So you have a state which is this psi CLR, which is a state of the bulk fields in the cosmology, the left and the right regions. I'm taking a projection on the cosmology with this OC that I defined here, okay? And then the other part of the state, the part of the state that is in the left and right ADSs, gets mapped isometrically into the left and right CFTs. This is like the structure of the encoding, basically, okay? So it will be useful to allow ourselves a bit more freedom and allow ourselves to actually change the matter state in the cosmology, okay? So to model this, what I'm gonna do is, in this Euclidean preparation, you can think that I'm adding local insertions. So suppose I do, if I don't have this blue line, it's exactly the thing I was discussing before. What I'm doing now is I'm adding like a local insertion. This is a local primary, which is sufficiently heavy to follow a geodesic in the bulk. And this geodesic travels through the cosmology, okay? So this is like a model of changing my matter state. I'm adding kind of particles in the cosmology, okay? The encoding is basically the same, but now I view it as a map. From the set of matter states that I can create like this is this M Hilbert space, and these states are being mapped to the CFT, to the left-right CFT through the map I discussed previously, okay? So some notation, so M is gonna be like the matter degrees of freedom, this OB, and you will see why this name in a moment, are the degrees of freedom that are entangled with the external ADS regions, and then LR are the basically external gases, okay? So we will consider K such states. You can consider different states by doing different insertions, different positions. You can use different primaries, okay, whatever you want to do. And we will study their CFT overlaps. So we will try to compute the overlaps between these states, okay? So these states are the images under the map of the corresponding bulk states. And I'm going to take K states, which I will suppose it's much larger than the entropy between the cosmology and the external regions. I should, so this is not needed, okay? You can do also the opposite case in which you have few states, you consider few states, but it's more interesting this one, and I just want to discuss this one, okay? This is just to simplify the discussion in what follows. Now, using the semiclassical gravitational path integral, you can compute statistical information about these overlaps, okay? This is one of the lessons of the past 10 years or so. So it's, in this setup, it's particularly simple to do these computations if you take the mass of the shell to be large. So to be in the region in which you have like a very large cosmology, which is super ADS. This is for convenience, simplifies calculations, and I'm gonna use it, okay? You can do also the other regimes, but this is simpler. So when you compute the overlaps, basically this is the same plot I had before, like the same figure I had before, but I'm kind of drawing it in a more suggestive way for those that are used to think about like closed universes, where typically like diagrams are drawn like this. So this prepares a cat, and this prepares a bra, and I'm taking the overlap, okay? And these are like the exterior regions, and this thing in the middle is kind of the cosmology. So I can compute an overlap with a gravitational solution, and this is proportional to delta ij with some normalization factor, not very important, okay? Now, if you compute the square of the overlap, there is a disconnected contribution, which is the square of this, of course, but there's also a connected contribution, which is like a wormhole, okay, that connects two copies of this in a different way, that makes like a connected geometry, okay? And the result of this is proportional, it gives you a result that is basically like this. Details are not very important, I'm just telling you that you can do these computations in gravity, okay? Now, these results are exactly reproduced if you use the previous model of the encoding, and you take this OC to be Gaussian random. Okay, you can do the same computations in this tensor network model, take this O to be Gaussian random, and you reproduce exactly the same results. Okay, so the gravitational path integral, what's doing, it's basically computing a microscopic average over an ensemble of CFT shell operators that are Gaussian random. Okay, this was studied by Martin as well in this paper. Okay, more in general, like in other situations as well. Okay, so from this, you can draw a couple of conclusions. One of them is that the overlaps fluctuate depending on which particular instance of the microscopic operator you have, but the fluctuations are suppressed by the entanglement entropy, by the second range entropy technically, with the external ADS regions. Okay, so if I have a state which has a lot of entangle, these fluctuations are very small. Okay, and doing another computation, which is a bit more complicated, but can be done, you can show that the rank of this matrix, so the number of states that you are generating in the CFT, is e to the second range entropy of the external regions, okay? So even though I started with k states, which are many more than e to the S2 of rho LR, I only get these many independent ones, okay? This is like the typical characteristic for a non-isometric map. I'm non-isometrically encoding the cosmology into the conformal field theory, okay? Now, connecting with Misha's talk last week and with the results in this paper, you can interpret this setup as an example of their general framework to deal with observers, okay? And how do you do this? So this is why I call this op. So this is basically like the results I had in the last slide, and I'm just gonna make some interpretation here, okay? So M here, like these degrees of freedom, are some matter degrees of freedom that I can imagine, that I want to imagine that I will be an observer inside the cosmology, and I want to probe these matter degrees of freedom, okay? The external ADS entangled pairs, so these LR here, are like the clone degrees of freedom that they introduced in this paper, okay? And this clone, what it does is that if you trace it out, it gives you a mixed state for the observer in the cosmology, which is diagonal in a certain basis, which they say it's a pointer basis because like it comes from the coherence with environment or whatever physical process, okay? In general, in our setup, this state is diagonal in a basis that can or cannot, or may not be a pointer basis, okay? But you can construct the entanglement in a way that you get something which is diagonal in a pointer basis, for example, the position basis. You can introduce these entangled pairs to be localized in position, and you get a diagonal matrix in position, which you can imagine that is a consequence of the coherence with some environment or whatever, okay? So, okay, for the people that were not here last week and maybe are not following this, this is not very important. I'm just trying to make a connection with Misha's talk. The point is that that language can also be used in this setup, and it's basically analogous, okay? And so it also kind of highlights the fact that what it allows, so the reason we have a non-trivial Hilbert space from the CFT that's encoding the closed cosmology is because we are entangling the cosmology with an external copy. That's the basic physical mechanism that allows you to have a non-trivial Hilbert space for the cosmology somehow, okay? Okay, you can do more elaborate models of the closed cosmology. I'm just showing this here because it's nice, I think. So it's conceptually the same thing as before, but it's kind of with more stuff in it. So you can add multiple shells, for example, and then you can do a preparation of a state in which you use 2 shells, and the geometry now looks as follows. So I have my ADSL and ADSR, just like before. I have these regions which are the same as before, but now in the middle, I introduced some Euclidean evolution so that the bulk saddle here, it's a black hole. Okay, it's this para-Euclidean black hole, and this is the Lorentzian continuation. So if you look at the time reflection symmetric slice here, and you look at like how it looks, you have the L, you have the R ADS regions, but now the cosmology kind of like the spheres go up, go to the shell, then they decrease up to the Einstein-Rosen bridge of the black hole. So there's like a bottleneck here, and then they go up again, and you get like this nice geometry for the cosmology. Okay. So now suppose you do the same computation as before, and you compute like how the overlaps fluctuate. Okay, the result is a bit more complicated, and I don't want to discuss all the details of what this means. So let's take a simplifying limit. Suppose I cut this entanglement, okay? Suppose I say, okay, I'm not entangling at all with the left-hand side. So what this means is that the terms of rho L disappear here, and then assuming the other 2 entanglement entropies are sufficiently large, this term is going to be very subleading, so we can forget about it, okay? So the overlaps now, the fluctuations of the overlaps are now suppressed by 2 terms. One is the entropy, has to do with the entropy of the observer, so the entropy of the external ADS gases, like before. But the other one is a geometrical term that has to do with this bottleneck in the geometry, okay? So again, for the people that were here last week, this is probably reminiscent of the e to the minus s naught that Misha had in his talk. Like there's a geometric feature of the closed universe, which is also limiting like the size of the Hilbert space that you can have, okay? So geometric features of the universe get also appear here in this kind of models. Final word on the holographic encoding, oops, sorry. Final word about the holographic encoding at large entanglement, okay? So the encoding, it's actually very similar to that of the black hole interior after the page time, which is also a non-isometric encoding, okay? This was discussed in detail in this paper in 2022, and I just copied here a theorem for that paper, from that paper. Okay, let me try to digest what this theorem says, and I'll explain you why this is important here, okay? So this theorem tells you the following. Suppose you have three Hilbert spaces, small a, b, and b bar, okay? And you have an encoding from a to b times b bar. Okay, how this is to be thought in our situation is the following. A is the matter Hilbert space, the thing that I'm encoding. L is this map. B is the CFT Hilbert space, and in my case, there's no b bar. Okay, the b bar factor is trivial in this situation. And now, suppose you have a unitary operator acting on the matter here, W. Okay, and you have some state of the matter. And then the following 2 conditions are equivalent. The first one is the one that you want. Okay. And what does this condition say? So given a unitary operator W here, there's another operator WB here in the CFT that basically acts in the same way on the encoded state as W acts on the matter state. So this is telling you that there's an operator in the CFT that reconstructs the action of a given operator in the cosmology. Okay, this is the meaning of this first condition. Now the second condition is a technical condition which basically measures the fact that b bar has no information about the action of that operator, okay? Not very important, the technical details of this, but in our setup in which b bar is kind of trivial, this boils down to the fact that the overlaps don't fluctuate much, okay? This is the analog of the, you can mathematically show it, and then this tells you that if these fluctuations are small, then you can, with very good, in a very good approximation, reconstruct operators in the cosmology, okay? So what this theorem is saying, applied to this setup, is that if you have large entanglement, so that these fluctuations are suppressed, you can reconstruct operators in the closed cosmology from the CFT. And it's a reconstruction which is state dependent. It depends on the state of the matter. This is exactly the same that happens in the interior of the black hole, okay? It's exactly the same kind of discussion. And in a sense, this is telling you that you can think of the closed cosmology as a model of a fully evaporated black hole, okay? So suppose you, this is kind of, okay, this is not very well defined, but let me just mention it. So suppose you take, like in a black hole that's evaporating, a Cauchy slice that is part in the interior up to this point, which has Planckian curvature, so you should be worried that things go wrong here. And then I take the other part of the Cauchy slice to be something which is after evaporation, okay? So you can think of this like as a cosmology disconnected from this region here, okay? So this is what this setup is modeling somehow, with the good feature, with the added feature that we don't have large curvatures at all in our Cauchy slice, okay? In the closed cosmology, you avoid the problem of this point. So it's kind of a nice model of that, okay? This is just like a suggestive way of thinking. I'm not gonna make much contact with black holes, but just wanted to mention this. Okay, so any questions before I move to the next part?
The amount of entropy that you are able to reconstruct is the entropy of the black hole, but somehow it's a different number from the size of the cosmology, right?
Yes.
So in the case of the cosmology, what is this entropy of the black hole? What is is something related to the observer?
Well, so in the black hole, if you let it evaporate completely, somehow like the entropy that you naively think you have in this state is the entropy of is equal to the entropy of the black hole, right? Like the size. So yeah. The entropy of the black hole. Sorry. So here it's by you define that in the construction. It depends on how much entanglement you put with the stereo region, which, if you want to use the languages of observers, is the entropy of the observer. But it depends on how you construct the states.
So somehow you can reconstruct only the amount of degrees of freedom that the observer has, something like that.
Something like that. And you can also, okay, so what I'm gonna do now actually is basically, so this encoding was dependent on having a large entanglement with the external ADS regions as we were discussing. And what I'm gonna ask now, and this is like the more speculative part, is what happens when we lower the entanglement. In particular, I can prepare the states in a way that the cosmology is not entangled at all with the exterior ADS regions, right? And then what does this mean? What is this? Can we still learn anything from the CFT, or does the universe just disappear and it doesn't make sense at all? I mean, and I think if you wanna defend this position, you should explain also why it disappears, because it's a large universe. In this slice, there are no large curvatures. It's all, in principle, looks fine. What's the physical process that makes this disappear? Okay, I'm not gonna defend this position. I'm actually trying to defend that we can still learn something from the CFT, but I'm happy that people may have other opinions and discuss about that. Okay. So let's cut the entanglement at all. Okay. So if we cut the entanglement at all, how do we do this? We can think of this as keeping the setup that I had before. One way to do this is that you prepare a state on L and another state on R, and you basically disconnect this from the preparation of the state in the cosmology. What this means, like a simple way to understand this is that you do infinity Euclidean evolution here, okay? So you do like, you take this beta to infinity, this beta to infinity, the other betas to infinity, and then what happens is that everything gets projected in the vacuum and there's no entanglement between the external ADSs and the cosmology, okay? This is a simple situation in which you can have that. But you can do more general things. You can prepare just a state here, and then you just compute here like some matrix element of the operator O, okay? If you use the same language we were using before, the state from the CFT now looks like this. So I have a state between L and R, and I have some number here, and this number is basically the matrix element of the shell operator, okay? Now, if I do many states like this, suppose I start changing like the way I prepare this state here and this state here. So this is the analog of what I was doing before of adding particles, for example. This is a way to think about this. And I compute also a gram matrix, so a matrix of overlaps between these states. Okay, from the CFT, it's obvious what happens, right? I mean, you can do it right here. So these parts give 1 because they are states that are bracketed with each other, right? And then I get some numbers, which are these matrix elements, OI and OJ star. By the way, so this big I and big J is just like a collective index for this II prime, which is basically the state that I'm putting on the left and right. Okay, it's just a way to simplify notation. Now, this matrix has rank 1, okay? It's obvious from this form of the matrix, right? It's a product of a vector with a covector somehow, so this is a rank 1 matrix. So what this is telling you is that the number of different states that you get in the CFT by encoding the cosmology like this without entanglement is 1. You always get the same state, okay? So I want to say that this is the manifestation of the one-dimensional Hilbert space of the closed universe in this setup. And what it means is that from an external perspective, so from the CFT Hilbert space, all closed universe states become indistinguishable once you don't have entanglement with them, okay? So this is like a manifestation of this fact. Right, I don't want to say that everything is lost yet, so let's try to take a bit of a different perspective or try to push a bit of a different interpretation here. So suppose we say that the main lesson of the holographic encoding that we had before with entanglement is that the bulk state of the fields within the closed universe is always projected into a fixed state. Okay, what my map was doing before, if you remember, is I had like a state OC, and I was projecting down the part of the state that was the part of the state in the cosmology, and then the remaining thing I had was some entanglement with the CFT that gave me some state of the CFT. That was how the map worked, right? What if this projection is actually like an important physical process that is happening in the closed universe? Okay, so you can think that my picture before was, if you want, like a picture at t equals 0, but you could think that this is a projection that is happening like at the singularity somehow, and you are kind of evolving back to t equals 0 to view it like this in the map. Okay, so this is very similar to the final state projection that Gary Horowitz and Juan Maldacena discussed for the interior of the black hole at some point. Okay, like more than 20 years ago, but somehow like the motivation now is coming from how the encoding works. Okay, so I'm saying that how we understand this encoding is motivated in this final state projection proposal. Okay, in the case of these cosmologies. Now, if we believe if we believe that there's this final state projection which is important, blah blah blah, can we learn anything about it? And the surprising thing is that actually the CFT fixes the final state in terms of the operator that's supporting the closed universe. So the CFT is somehow telling you what's this final state. Okay, and I think this is cool, and this is why I think it's worth pushing this interpretation a bit. Okay. So how does this work? Okay, suppose you focus just on the part of the closed universe, no entanglement. Okay, as before. Suppose I'm preparing like a state on the VCFT, which is this psi I, and a state in the CCFT, which is this psi I prime, right, by some Euclidean procedure. And then I'm including this shell operator. This is like the CFT picture. In the CFT, what I'm doing is this projection, which basically amounts to the matrix element of the shell operator, okay? Now, if I have a bulk picture, this psi I is preparing here some state small psi I in this region of the ADS. And this psi I prime is preparing some psi I prime here. And if I take the shell to be very, very heavy, the shell basically lives in the asymptotic boundary, right? So it's like this picture is kind of adequate in that case, because like it's like I prepare something here, I prepare something here, I map it to the boundary with this tensor network, and then I input like the shell operator. And in the bulk, this is computing this projection. So the state that I prepared, the B and C state that I prepared, which I collectively denote by this C big I, is being projected down to this OC that I introduced before, right? So somehow, so the final state, as seen in the bulk effective field theory, you can expand it in a basis of the bulk effective field theory with some coefficients. And what I'm saying is that these coefficients are fixed by the matrix elements of the shell operator. Okay, so this is how the CFT information, so matrix elements of the shell operator, let me say, in low energy states, because these states are all low energy, are all states of like particles in ADS, okay? These matrix elements are basically fixing the wave function of the final state in the bulk effective field theory, okay? So this is, I think, like the surprising / nice thing here. And furthermore, one extra, okay, so let me emphasize this. So a given universe with a given singularity is defined by choosing a global final state, so by choosing the operator that supports it in this setup. But let me say also another very nice thing of this construction, which is that this proposal connects the structure of the singularity, you believe that this final state is related to the singularity, to chaotic properties of the CFT. Why is this? Because we said that these matrix elements of the shell operator are basically taken from a typical draw from a Gaussian random ensemble. Okay, so they are very random, these matrix elements. So this final state is very random, as seen from the effective field theory, from the low energy bulk effective field theory. Let me make a comment here, which is that these matrix elements are matrix elements in low energy states of an extended operator, which is a thin shell operator. Okay, so this goes beyond the standard ETH proposal somehow, but but this conclusion is supported by gravitational computations of higher moments using Euclidean wormholes. Okay, so you can study the higher moments of this operator, and you see that they are well approximated by a Gaussian ensemble. Martin did this in 2022. Okay, so what's the proposal? That this final state is fixed by CFT properties, by information from the CFT, and due to these CFT properties, this state is very random. Okay. Now, why is it important that it's very random? Okay, it was already important in the final state proposal of the black hole of Horowitz-Maldacena, actually. And the reason that it's important that it's random is that the modification of quantum mechanics implemented by the final state is hard to observe, provided this state is sufficiently random, okay? So, okay, this is gonna be like a very quick slide about what final state quantum mechanics is. It's a modification to quantum mechanics, and okay, I don't want to enter into too much detail of this because I don't know, I'm probably still too young to do that, and I want to get a job, so I don't want to talk about modifications of quantum mechanics too much, okay? But if you assume that there's a final state modification of quantum mechanics, I can quickly explain why having a random state is kind of important, okay? So what's standard quantum mechanics? Okay, in what's called the consistent histories formulation, you can define a functional, which is like the decoherence functional, which is basically, suppose you want to make some measurements, okay? And this can be generalized a lot, but I'm just going to consider one measurement, okay? Suppose I'm measuring position. And position has several possible outcomes, which I'm labeling by lambda, okay? So I can have like, lambda means a particle here, lambda prime a particle there, so these are possible different results of the measurement, okay? With each result, I have a projecture associated, okay? How do we compute probabilities in standard quantum mechanics? We compute this for a possibly mixed state. So if we have a state, rho I, which can be mixed, we compute this thing, which basically looks like this. Okay, and you see two things. First of all, this thing is diagonal. It has a delta lambda, lambda prime. And the second thing is that the value of this thing is like the probability of measuring lambda, what we would usually call the probability of measuring lambda, okay? So the fact that it's diagonal is important, and you can show actually that this decoherence functional, which is something that can be introduced in more generality, has to be diagonal so that you can assign probabilities, okay? And when it's diagonal, you assign probabilities for a given outcome to be the value of the d lambda lambda for that value, okay? This is how you assign probabilities in quantum mechanics. Final state quantum mechanics is a modification in which you not only have an initial state, you also have a final state. Okay, it's a more time-symmetric formulation of quantum mechanics. This was discussed a long time ago and in the 90s as well by Gell-Mann and Harrell. And okay, so I can define this functional here, and the story is basically the same. If this thing is diagonal, I can assign probabilities, and the probabilities are given by the diagonal elements of this thing, okay? So this is all I want to say about final state quantum mechanics. Now, suppose I have an observable on a small subsystem, okay? So I take my cosmology, I assume that my cosmology is governed by some sort of final state quantum mechanics like this one, and I just want to look at the small subsystem. So my cosmology, I have like the system I care about, which is small, and then I have another system which is much larger, okay? There should be bars here, so S bar is much larger than S. Since my state is random, to a very good approximation, this is a well-known result by Page, the reduced state on the system is basically maximally mixed. This is a consequence of the fact that my state is random, okay? And then if in the subsystem I care about, I have a state which is maximally mixed, you can put an identity here and you realize that you recover quantum mechanics. So final state quantum mechanics becomes normal quantum mechanics for a small subsystems, provided my final state is sufficiently random. And this is why it's important that the final state is random, okay? So just to recap and to emphasize the important thing, the randomness here came out of the CFT. So I think that's also pretty nice, okay?
5 minutes.
Okay. Right, so not everything is roses in this formulation, and there are some things that are weird, okay? So let me just mention one that was emphasized by Stefano and Pratik in this paper in 2024, okay? So if you take this final, so they were not discussing this final state interpretation or so on, but we can reformulate the things in this language, okay? So if you take this final state interpretation seriously, it seems to lead us to accept that the map between bulk and boundary state is not unique, okay? There can be several bulk states mapped to the same boundary state. Why is this? Okay, I've been discussing this state here, where I have a left ADS, right ADS, and a cosmology, and this is entangled within left and right ADSs, okay? And it's encoded like this. Okay, but the encoding involves like a final state projection in the cosmology. I can do that final state projection at the level of the effective field theory state here, right? And then what I get after I project is a state just on the left and right. The pattern of entanglement can be much more complicated, but this is a state which has no cosmology at all, right? And this is a state which we know how it's encoded, like these states get mapped to the left by the usual isometry, and these states are mapped to the right by the usual isometry. So these two states are basically dual to the same CFT state, okay? This is probably a bit different from what we are used to thinking, okay? So this is, I think it's an unavoidable consequence of what I said before, but it's what it is, okay? Right, I don't have much time left, so I think I'm going to skip the coarse graining part. So this was just a different way to see the cosmology. Okay, let me just make some quick points here. So in light of the thing I just said, it might be tempting to completely dismiss the bulk state that includes the closed universe. I think there are good reasons against that. One is that at large entanglement, we showed that the expectation values in the interior can be accessed from the CFT, much like one would do in the black hole interior. This was like the encoding I discussed when entanglement is large. The Euclidean preparation also suggests the existence of a large closed universe, and it has no good reason to disappear, right? I mean, I don't know why it shouldn't be there. And in particular, this point can be made more sharp by constructing CFT experiments, which involve coarse graining. If you coarse grain, you can very easily connect coarse graining over the operator that sustains the cosmology, I mean. You can very easily connect with path integral results. And those path integral results are related to the geometry of the closed universe, okay? So the closed universe somehow probably has some meaning. I'm not going to give the details of this. These were my next two slides, but I don't have time, so let me just make the final comments. So let's recap what I presented. So we have reviewed a construction which naturally gives geometries with closed universe, and in a very standard idea CFT setup, okay? This cosmology is supported by a matter shell, inserted by a specific CFT operator. At the very least, the geometry with the closed universe captures properties of the CFT coarse grain over the specific microscopic of the shell operator. This is what the path integral tells you, okay? Now, if the cosmology furthermore is highly entangled with the external regions, a more standard non-isometric encoding emerges. And in a sense, the closed universe is analogous to the interior of an all black hole, but without large curvatures, okay? And if you go a step further, the construction suggests that for a particular instance of the shell operator, a specific final state projection is implemented. And this final state projection is fixed by the CFT data. And the good thing is that it still allows like standard semiclassical physics in small regions, like normal quantum mechanics in a weakly curved background, okay, somehow. So some questions, open questions, like thoughts for discussion, some of them crazier than the others. Is this final state projection present for every singularity? That means that in any cosmological or black hole-like singularities, you will have some sort of this final state projection. And can we always characterize them from properties of the CFT? I think that would be nice. So the closed universe that we discussed has a finite lifetime. Actually, I didn't mention this, but the shell collapses on itself, like destroying the universe on a time scale which is of the order of the ADS scale. So it's short-lived, this cosmology, okay? So what happens if you have like situations that eternally expand? Like, do you have also final state projections? I don't know. So a point which is confusing and that I have to admit that I don't fully understand is that what we did requires a large N limit in which we only discuss small perturbations on top of a classical geometry supported by the thin shell. And that background is kind of unchanged. I cannot add, change the shell operator too much. So what happens when we go away from this? I think this is kind of a confusing point that, one should clarify. And now, like the final, like almost crackpot comment is that should we use final state quantum mechanics to describe the experience of an infalling observer in the black hole or an interior observer in the cosmology? And this has a lot of problems because, like, if you do the final state projection and you take it seriously, so causality is affected because there's like a final state that's kind of projecting information back in time. So these final state quantum mechanics can be very problematic, okay? But I just wanted to mention this. So thank you very much.
Excellent. Thanks for the very nice talk. So questions, yeah.
It's me. So I have a basic question about your gluing procedure. So so you connect to